Okay, so last time we were talking about the pressure composition phase diagram. So we did these px curves here. So if you remember, we had pressure on the y-axis. And so over here, this is the composition and mole fraction. So when the mole fraction is 1, that means all of the moles in this flask are substance A. And when substance A's mole fraction is 0, then it's all substance B. And we just do AB. We don't really, it works for any compounds, any pair of compounds. And that's the vapor phase. Now, above that line, you're at higher pressure. And so what's going to exist at higher pressure? That's going to be the liquid phase. So that's a little confusing for folks. Most people think the liquid would be below the vapor. But in a pressure composition curve, the higher the pressure, the more liquid you have. And then here is the region where you have equilibrium. And then down here is the vapor. So at low pressure, naturally you would have vapor. In between, you have two phases in equilibrium. And so just as a review, let's take the liquid. We'll sit right here in first. Okay. So if we had a 50-50 mixture and we come down at this point, we start entering into vapor liquid equilibrium. And so then we have vapor that's rich in A. That makes sense because A is the more volatile compound. It has the highest vapor pressure. So the vapor above the 50-50 mixture is like 65, 35 A, 65% A. If we keep lowering the pressure, more of that liquid is evaporating. And since that liquid the vapor is rich in A, to see the composition of the liquid moves left. So if we're right here in the middle, we have about 50% of the moles in vapor and 50% of the moles in liquid. So there's that lever rule. Whenever we talk about equilibrium, we have the lever rule examples. And so when we're right in the middle, we're at this pressure right here. Somehow we're in a container where we can maintain the pressure. And so we have 50% of the moles in the vapor, 50% of the moles in the liquid. Then we get to this point where we're sitting right on that vapor composition line. And at this point, it's 100% vapor, 0% liquid. So that last little droplet, because we're dropping the pressure, that last little droplet's about to evaporate. And if we keep lowering the pressure, maybe we're doing this with a piston or something like that, then we're down here in the vapor phase where it's 100% vapor. We're just lowering the pressure. And so this two phases in equilibrium, that's the VLE region. Let's do VLE, vapor liquid equilibrium. And that's the general description of this science. So if you're dealing with, phases and liquids and gases in equilibrium, you're dealing with VLE phenomena. Okay. Any questions on the PX diagram before we switch to TX? Notice these pressure lines are at a given temperature. So this is a particular slice. If we had the temperature axis coming out this way, this is a particular slice through that temperature axis. Okay. Now, when we go to a temperature, if we look at the temperature axis versus composition, we're dealing with a TX phase diagram. And now instead of pure vapor pressures, we have boiling points. So this is T boil for substance B, and this one is T boil for substance A. Does that make sense? Pure A, you got a boiling point. Pure B, we got a boiling point. Okay. Now these are the same substances. So notice A is more volatile. And so it is a lower boiler. That makes sense too, right? The lower boiling point is going to have the higher vapor pressure. we call it boiling. A normal boiling point is when that vapor pressure equals 1 atmosphere. So this whole diagram on your right is the diagram, the boiling diagram. It's at 1 atmosphere. So every one of those mixtures has a different boiling point. This is all of the temperatures at which the vapor pressure is equal to 1 atmosphere. And also at low temperature, we have the liquid. So they're reversed in the TX diagram. The bottom part of the graph is liquid, and the upper part of the graph is gas. Because if you raise the temperature, you're going to boil it all away and you have a hot gas. If you cool it down, you've got a cold liquid. And then here you have this 2 phases in equilibrium. So let's take our 50-50 mixture and let's increase the temperature. So when we hit here, it starts to boil, and the vapor pressure is enriched in A because it's the lower boiling substance. So this is the composition of the vapor phase. If we have it in a container, we keep heating it up, we're going to move straight up this line, and this line right here would represent Z, right? Z, A, this is YA, and this is XA. Let's say we're right here in the middle. We've got 50% of our moles are in the liquid phase and 50% of our moles are in the vapor phase. And if we keep that same composition in the flask, we get up here, we're at such a high temperature now, we have very, very little liquid and everything is in the vapor phase. And then when we get above that line, then it's all vapor phase. So that's the how to use this phase diagram and read all the different places. So let's say I tell you you're right here. Describe the system. You would say we're in the liquid phase, right? If I tell you you're right here, at this point right there, I would say describe the system. Well, you're right in the middle of the vapor and liquid equilibriums. You would draw horizontal lines, and wherever you hit those lines, the length of those lines would tell you the relative compositions of those phases. Okay, and it's that lever rule problem. So if you're right here in the middle, it's easy because you're 50-50. You got 50% in the vapor, 50% in the liquid, and so this region right here would be that lever rule region. Okay, so this right here. Let's pick this one right here and do it. So let's do the lever rule on this one. So we've got XA, and let's say our fulcrum is really close to YA. See all three there? Okay. And remember, this is a seesaw, so you've got a really big kid on this end, and you got a little bitty kid on this end to get it to balance. You can do it with masses, whatever. But the point is that this short end times the big kid is equal to the long tie line times the little kid. So NXA times length A, or length, let's call them 1 and 2. How about that? Need my eraser. Tablet's not going to play with me today. Okay, so we've got number of moles 1 times length 1 is equal to number of moles 2 length 2. So for those to be equal, if I've got a really long line for L1, then I've got to have a small number of moles. And I've got a really long, really small or short line 2, then I've got to have a really big N2. So that's the lever rule. Okay, what if we start removing this fraction of YA? Then we're distilling. That's distillation. And so this is how we distill liquids and separate them. We've done this in organic chemistry. So here's a fractional distillation column. We have the pot down here. We've got a temperature gradient. There's a metal chain in there to give it some surface area and to keep currents from developing. Sometimes you can get poor separation if you just have like a flow of gas through there and it's not really interacting with the temperature gradient. It's kind of like a cumulus cloud, a thermal vent that you get outdoors. You could have that same thing happen in the distillation column where you just get a pump and it doesn't give you good separation. So you want something to slow down the flow and have lots of collisions with the walls of the glass. But you can see this is a brighter color than up at the top, so it drops. This orange region in the middle is only there because there's a jacket around it. So there's a glass jacket right here that's kind of messing up with the temperature view from the infrared camera. But it's hot down here. It's the pot down at the bottom, and then the condensate temperature at the top. And then we collect that condensate. This is the fractioning column, and that's the still bottom, also called the pot. Okay. So we need to know these terminologies because I'll be asking you what's in the pot, what's in the still bottom after distillation, what's in the collection flask. Okay. What temperatures would you have here? So we're going to use the TX phase diagram to understand distillation. And that's the boiling pot temperature. So we have the condensate temperature at the top, which is cooler than the boiling temperature. And so this is what we have when we do this separation. As we go up in the phase diagram, this is in the pot. And we're boiling this mixture. Now the low boiler is going to be in the vapor phase, going to be concentrated in the vapor phase because it has a lower boiling point. So we're going to have lots of that substance in the vapor phase. So it travels up the column and condenses a little bit because you get a temperature gradient. It gets away from the heating mantle. The glassware is cooler, so it hits the glassware and it turns back to a liquid. So when it turns back to a liquid, what happens in the phase diagram? It drops down here. And so it becomes this point. So you have vapor, and then you have a liquid drop. On the wall of the glass. Now what's it going to do? Gravity is going to pull it down. So it's going to drop a little bit more, and it gets hotter as it goes down the glassware. And so what's going to happen is it's going to reach a point where it's going to evaporate again. It may not go all the way to the bottom of the pot. It just has to come down the chain or the wall or whatever a little bit and get warmer, and it's going to evaporate. And so then when it evaporates, that vapor is enriched in A even more, or B. I keep saying A, but this is B. So it's enriched in B. And so it's a little further up the column because it took it further up to get to a colder temperature where it would condense again. And so these liquid drops form all the way up the column, and they start to run down, and then they re-evaporate. And it just keeps happening until you get hit the collection flask. Now, ideally, this would happen all the way down, and you would get pure B out. If you have a really long column and lots of surface area on the way up, then pure B would come out, and you would have what they call a higher number of theoretical plates. You'd have more plates that they would go through in terms of this recondensation, and then they would come out a purified substance. If you've got a tighter column with more packing and so on, you would get a better separation, and you would get more pure product out. So let's talk about these plates, okay? So this is what I'm talking about when it's compared to a fractional distillation column. So up here is the 128 Fahrenheit, the boiling point of the pot. And then way down here, as it goes up the column, you see all 5 of these condensations here. There's a temperature gradient. So do you see how it's labeled on the column? These different condensation points. So after 1, we get condensation. After 2, we get condensation. 3, 4, and then 5, we get the condensation in the condenser. This would keep going if we had a longer column. So we would get more and more plates if we had a longer column. and more plates if we had packing material in there. And so this was a particular distillation we did in the lab. It was 128 degrees in the pot, 105 degrees up at the condensate temperature. And so this is the low boiler coming out into our collection flask. Now these plates, we've been talking about theoretical plates. That's a useful terminology, but the word plate goes back to the refineries and bubble plates. They're no longer used in academia, but they are used in refineries. And so more plates equals a better separation. So this is what sort of a artist drawing of what's happening at a refinery. So these are called bubble cap plates. And it was hard to find pictures online for these bubble cap plates because it was old technology, not a lot of pictures online. I went and looked last year, and all of a sudden I saw tons and tons of brass and copper bubble plate setups. And it's because people are getting more into whiskey and distillation and distilled spirits. And so this is like a renewed interest. People will have these small stills and be distilling spirits. But this is what happens if you look. See, there's this little weir. This is a term that you need to know. It's a little wall above which the liquid, when it gets higher than that wall, it'll flow over that wall and go down to the plate below. And so that's this weir right here is this point right there. Now, what about the bubble plates? Remember I said for efficient distillation, you need a lot of interaction of the vapor with the liquid on the walls or in the packing material. And the bubble cap plate forces that interaction to happen. So the bubbles here are below the surface of the liquid. The little bubble vents. So these are the bubble caps, and the vapor goes up into that cap and then comes down and it bubbles out below the level of the liquid. So you have lots of interaction of the vapor and the liquid. And that's what we're trying to do, is vapor-liquid equilibrium. Now, if this has got a substance that, is, liquid or right at liquid at that temperature, then it's going to stay in this region. And when we get too much of that, it's going to go down here to this warmer temperature. And maybe that's too hot for it, which it'll evaporate up and go back up here. So we'll get this equilibrium stream of liquids that boil right around this temperature range. And they'll be stuck right there at that temperature range because that's their boiling point and condensation point. And so then we can collect those fractions. We can have a gasoline fraction. We can have a diesel or kerosene fraction. We can have down here a heavy oil fraction. We can have up here a light fraction, a white gas fraction, even liquid propane and butane out the top. So we can have all of these different boiling point fractions. So that's why if you were to look up gasoline, and I encourage you to do this, go on Wikipedia and type in gasoline. What's the composition of gasoline? It's hundreds or maybe even thousands of compounds. Well, they don't make gasoline synthetically, right? It's a distilled crude oil. And so there's a range of boiling points where those compounds will collect on that bubble plate and they'll be tapped off and pulled into a tank. And so this is what's going on at a refinery. You see these really tall columns, those are distillation columns. So those are fractional columns or fracking columns or fractional distillation columns. And you can see that's the fractioning tower. And then you have these maintenance platforms where people can go up there. They can also pull samples. Let's say they want to pull a sample to make sure they're getting low sulfur diesel or something like that. They can go and they can pull a sample and go analyze it. And then here's a fraction tap coming off. This one does not seem to have a lot of taps on it, so it's maybe just a particular separation that just has two fractions that they're interested in. But here's a simplified drawing of most of the important processes at a refinery. Up here at the top, these gasoline vapors are liquid petroleum gases. So, if you get a butane lighter, you can see that little liquid down at the bottom. That's butane. It's a liquefied petroleum gas. It wants, at room temperature, it wants to be a gas. It doesn't have a very high vapor pressure, and so it can be held in a plastic container. So it's held in a little plastic container. It's at high pressure, somewhat high pressure. That's why when you click the clicker, the flame is coming out pretty fast on a butane lighter. Yeah. And so that's the very top, the most volatile thing. Then we have the gasoline tap here. Some of that goes through various reformers or they clean up the gasoline and achieve whatever kind of mix that we want. Also notice that some of this medium weight and heavy gas oil down here, it has a lot of double bonds in it. The double bonds make it really dirty. It's a darker fuel, and it also oxidizes easily, and so it's not very stable. And so if you could hydrogenate that and put hydrogen on those double bonds, you make a more saturated fuel, maybe even break some of those long chain hydrocarbons and make more gasoline. Gasoline is the moneymaker, and so is diesel, but gasoline and jet fuel are the moneymakers. And so Wilkinson's catalyst, if you're in advanced inorganic, you'll talk about catalysis, and hydrogenating these double bonds in petroleum was how Wilkinson got the Nobel Prize. So he produced a catalyst that would crack some of these heavier molecules and make more gasoline. I heard that he changed the percentage of gasoline coming out of crude oil by just a few percent, 1 or 2%. It was worth billions of dollars. Just changing that, moving that needle 2 more percent on a billions of gallons of crude oil made it much more profitable and much better. Okay. And so then you have just different grades of fuel coming out of this. And then you have industrial fuel, really heavy oils. And then at the very last, you have this asphalt base. So this tar that's in the bottom of the still. You've pulled off all the volatile stuff, and you've got this really thick, viscous tar. And you take that and mix it with gravel and put it on the roads because it's waterproof. I mean, it's like a tarry, polymer almost. And you mix that with the gravel, and then it's a goopy mess. You spread it out on the road and press it down with a heavy flat roller, and then you've got your asphalt. So we try to squeeze every small thing we can out of the crude oil. A lot of this stuff too will go into base products for polymers. So yes, we might be able to get off fossil fuels for say transportation as an example. But all of our plastics are also fossil fuels. I mean, they're not fuels; they're plastics. They come out of the crude oil. So let's pause here and I want to make sure that you understand this diagram before we start messing with it. We're gonna change gears and start talking about difficult situations in separation called azeotropes. Does everybody understand this? B is the low boiler. So in a fractional distillation, what comes out? B. Okay. What happens to A? Well, think about it. If I've started here, and this is my pot, and I'm starting to pull out B, what's happening to the pot? If I can't pull B out of the pot and have the pot stay still in terms of its composition, what does it have to do? No, I'm saying its composition. What does the composition of the pot have to do? If I'm pulling B out of it, it has to move towards A. So the pot goes uphill. It moves this direction, which what I mean by uphill is it's moving uphill this way, right? As I'm moving, if I'm removing B, the pot is moving the opposite direction. It's getting more concentrated in A because I'm taking out the volatile compound, okay? And the pot boiling temperature will rise, and that's how you can kind of track it. As you're tracking the boiling point, you're tracking B, the B is staying there, and then all of a sudden this condensate temperature will dramatically change, and you pull that collection flask off because you've gotten all the B out that you're going to get, and the temperature will rise up, and eventually it will rise up to the boiling point of A. And then we're just boiling A and collecting A. So if you just sit there and boil the pot dry, your composition will go back to the pot composition. You'll get all the B off, and then you'll start boiling A over, and you'll sit at that boiling point of A until it becomes, dangerously close to boiling dry. We never want to boil it dry, but you can, and what you've done is you've cleaned up, because the stuff in the pot is the non-volatile residue, the stuff that doesn't evaporate, boiling chips, but also reaction products. We have oxygen in here. And so you heat up these organic molecules and oxygen will oxidize them. So you get aldehydes, ketones, more aldehydes and acids than ketones. Ketones are in the middle of the molecule. I mean, it could happen. If you have a double bond, you can get attack at a double bond. But the pot will move and become more concentrated, and I like to say it goes uphill. So look at this diagram. We're boiling the pot here, and the pot is going to move uphill. And the condensation flask, and the condensate is always downhill. So the downhill part is collected. That's an important point. Everybody, it seems obvious, okay? Let's go to azeotropes now, because this is a problem. Okay, so we've got this. Here we have a problem. This is an azeotrope, and it's defined as when a liquid and a vapor composition are the same. So this is the definition of an azeotrope. So here we are at this point right here, and we come up and look how these two vapor curves touch. So it's like we have two phase diagrams, and that's a good way to think of it. So if we were to split it right here at the azeotrope, we have two TX phase diagrams. So if I'm over here on this side, what's going to be collected? Pure A. That's the downhill piece. So when I boil this, this drops down here, bounces over, drops down here. So on a fractional distillation, this is a condensate here, and the pot moves uphill. You see how the pot would move uphill to that azeotrope? It would not go all the way to the left. It would not, the pot would never get past this point, because that's the highest boiling point, and it's the least volatile. So the pot's never going to evaporate until we get to that temperature. And so we're stuck there. What if I was on the other side? If I was on this side, if I was less concentrated in A, there we go. If I was over here, then I would come up here and hit the curve there, and B would be collected. It would bounce downhill, and then pure B would be in the condensate. See how confusing that is? It kind of depends upon which side of the azeotrope you're on as to what's collected. But then the pot would still move uphill, and the azeotrope would be in the pot. So this is called a high boiling azeotrope. Pretty cool, I think. So we have a high boiler azeotrope, because it's the highest boiling point on the whole diagram. The azeotrope is because you have that pinch where the vapor and the liquid lines touch. That makes sense? Wherever they pinch, that's an azeotrope. And if it's higher than either the pure substances, you have a high boiler. You could have a low boiler too. Low boilers are frustrating to organic chemists and other people because you can't separate the compounds. This one you can separate. If you're on the A side, if you're high on A, then A can come off. If you're on the low side, you have more B than the azeotrope, B can come off. So you can purify a little bit of A or a little bit of B depending upon which side you're on. But the pot would be stuck at the azeotrope. Okay, let's look at the low boiling azeotrope. Here's one, and water and ethanol is a famous example of that. You can't purify ethanol through distillation because there's a low boiling azeotrope. So here it is. So this is an example of water ethanol. So if we're over here, we're really concentrated in A. We boil that. The condensate drops down, and then the azeotrope comes over in the condensator because it's the lowest point. So this would be the collection flask. And then if we're on this side, it would move uphill. The pot would move uphill here. And so you may say, well, if we were trying to purify A, right? If we're trying to purify A, we boil off the azeotrope and the pot gets closer to pure A. But the problem is you can't use the pot as a pure substance. The pot also has the aldehydes and the alcohols and the oxidation products and the non-volatile residue. So you can't use the pot as a pure substance. It looks like on the diagram it would be pure, but the truth is the pot is never pure. So we have to, if we're wanting to purify substances, we're collecting the collection flask. That's the purest stuff. The pot may look like it becomes pure A, but you can't use the pot. It's dirty. So that's just the issue. Now, if we're below the azeotrope in terms of A composition, we have more B, then we would come up here, and sure enough, it would do the same thing. The azeotrope would be collected, but if we start over here, then the pot would move up to pure B plus all of the dirty stuff that's in the pot. Yeah. But either way, the low boiling azeotrope is the lowest boiling thing. It's going to be the thing that's collected. So in a low boiler azeotrope, the azeotrope is collected. You're talking about this little b here?
Yeah.
Yeah, the azeotrope, the low boiling azeotrope. No matter what, it's going to be collected. And so the lowest point, it's the lowest point on the diagram, and things are going to run downhill to it. Whereas over here, you kind of have two low points. If you're on the left side, it'll run downhill to the left. If you're on the right side, it'll run downhill on the right. Yeah. So a high boiling azeotrope can be frustrating too, but at least you can get a pure A out or a pure B, depending upon which side you're on. Yeah. So that's azeotropes, and that's a very important thing in cleaning in my research for vapor degreasing. So for vapor degreasing, we have a boiling mixture of solvents, and it creates a vapor of solvent vapor. And to keep it from coming out of the machine, they have refrigerated coils. So the vapor hits those refrigerated coils, condenses, goes back down into the pot and reboils. So it just creates this equilibrium of boiling liquid and its vapor. And then you put a dirty part in the vapor, and the vapor is pretty hot. It's at the boiling temperature, and the part is at room temperature, so it's cold. You stick it in there, that vapor condenses on the part and drags off the greases and oils, and those go into the boiling sump. And so then so also that condensing vapor heats your part up. So your part is hot. It's at the boiling point of the vapor. But then you lift it up. We have another cooling zone. You put it in these really cold coils, and the part is hot, and all the vapor comes off, and so it comes out dry and clean. It's a beautiful cleaning technique. They used to use Freon, which was an inert, non-flammable, inert organic solvent. It was just super good for cleaning hard disk drives and gyroscopes for aerospace and all kinds of things, medical equipment. But it depletes the ozone. So then they got rid of Freon, and they went to another solvent. We're like on our third or fourth generation of solvents. Well, they took away the non-flammable ones. So we started using flammable solvents, but you've got a vapor that's pure solvent vapor, and you got a room that's 20% oxygen. Somewhere between where the worker's standing and in there, you're going to have the perfect stoichiometric mix of solvent and oxygen. Very dangerous. And although you can say, well, we're going to electrically isolate this and not have any exposed wires, some metals are dissimilar enough that they will spark when they touch. And so the risk is too dangerous to have the risk of exotic metals and things when they touch and there being a static charge or something like that, setting off this explosion, burn your facility down, kill your people. So there's a requirement that your solvents have to be non-flammable. Well, they mixed in blends. So they took a fluorinated solvent and mixed it in with these flammable organic solvents and made low boiling azeotropes so that vapor would have the fluorinated flame retardant. and the good organic solvent. And yet it's constantly being boiled. But as long as you have a low boiling azeotrope, that vapor will recondense and go back in, and you're not going to break that azeotrope. And so now you can break it if you put enough oils and waxes in there. Now you got a 3-component mixture, and 3-component mixtures may have different phase diagrams. And so you might form an azeotrope with the fluorinated compound and the wax, and then your flammable solvent is now concentrated again in the vapor phase, and you got a dangerous situation. So they make you monitor your solvents and so on. We're getting away from all of that now because the good organic solvents, they're tamping down on those even further, and now there's pressure against the fluorinated compounds. You've heard of the PFAS discussion. Have you heard of those? The forever chemicals they talk about? Well, a lot of these organic flame retardant molecules are fluorinated compounds, and they're going to be under regulation pressure. 3M just shocked everybody 2 years ago and just said, it's kind of over Christmas break, said we're going to pull out of our fluorinated molecule market. And they walked away from billions of dollars of revenue because they could see the regulatory scrutiny on the horizon. That was a big deal. So here's all of the different types of azeotropes. It gets crazier, believe it or not. Molecules, nature, like my research advisor as an undergraduate, he was a really old guy. He was like, nature's a tough old bird. Nature does crazy things. And so we've talked about the top row, which is a low boiling azeotrope. And we talked about the third row, a high boiling azeotrope. Okay. Here's the PX diagram. Here's the TX diagram. So if it's a high boiler, it's got a low vapor pressure. That makes sense, right? And the top one, if it's a low boiler, it's got a high vapor pressure. So you could look at azeotropes in the PX diagram too. This is kind of a weird diagram. This is YX versus TX, or YA versus TA, YA versus XA. So notice here on the left side, the vapor of A is higher than B, and over here it's less than, and so it's kind of interesting. But where they touch, that's the azeotropic point. Now what we're going to talk about next in the course is these heterogeneous ones. Heterogeneous. So this is where you have phase separation, 2 liquid phases. So now it's getting crazy. We have 2 phases now. We have vapor and liquid. But then we're going to have vapor, liquid A, and liquid B, like 2 different liquid phases and vapor on top. And here we have azeotropes, which this is the only time you're going to see this. We have like a low boiling azeotrope and partially miscible liquids. So for over here, we have the lever rule between the 2 liquids, okay? And over here we have the azeotrope. If we're over here and we boil this, we're going to collect the azeotrope. If we're over here and we boil this, if we get above this line, then we have liquid A and some vapor B, and it comes down and has an azeotrope over here. It's just absolutely crazy. So here we have a double azeotrope. So that's weird. I don't know of any mixtures that have that, but it's a possibility where you have a low boiler here and a high boiler there. And if you start out in the middle, your collection flask will have the low boiling azeotrope, and your pot will approach the high boiling azeotrope. And nowhere, I guess if you were on the right hand side, your pot would approach pure A plus the non-volatile residue. And if you're way on the left hand side, you might be able to collect a little bit of that excess compound as a pure substance in the collection flask. And so that's pretty much all I've got for today. So we're ending a little early.